Okay, so I think it's time that we get started. It works. Okay, yeah. So I have the distinct pleasure to introduce a very special colloquium speaker. Professor Lisa Randall is currently the Frank Baird Junior Professor of Science at Harvard University. And she has also received her PhD from Harvard in 1987. She was an assistant professor at MIT, I think. Then she went on a tenure position at Princeton, back to MIT, and now at Harvard. So very, very interesting CV. Professor Randall is a member of the National Academy of Sciences, the American Philosophical Society, American Academy of Arts and Sciences, a fellow of the American Physical Society. She won a Sloan Research Fellowship, the NSF Young Investigator Award, the DOE Outstanding Junior Investigator Award. I could just keep going, right? But we want to hear from her, not from me. So I'm going to stop right here. I want to mention one more. In 2011, she was awarded a Doctor of Science honoris causa from Brown University. So I think we should mention that here. So her work is in theoretical physics, and she's got a lot of radical and crazy ideas that become mainstream with time. I think maybe the most famous one is published in 2 papers in 1999 with Raman Sundram, and it's about explaining how warped extra dimensions could solve the hierarchy problem, which is still a nut we're still trying to crack with experiments at the Large Hadron Collider, for example. So this idea has given guidance, and other ideas has given guidance to us experimenters for quite some time. And I remember myself searching with a student for these things, and I just looked it up. Together, these 2 papers are just shy of 15,000 citations. That's substantially more than the CMS Higgs paper has. So that makes her, I think, one of the most highly cited theoretical physicists. And in 2019, that's this year, she shared the J.J. Sakurai Prize with Raman Sundram for this discovery. So that's another one that I think I want to mention. So her talents encompass many dimensions, though. She likes to connect art and science, and she's written the libretto for an opera, and she's co-cured an art exhibit for the Los Angeles Arts Association. And in recognition of this dimension, in 2012, she was the recipient of the Andrew Gemmant Award for the American Institute of Physics, which is given to for significant contributions to the cultural, artistic, and humanistic dimensions of physics. She's also the author of several books. There is Warped Passages, Knocking on Heaven's Door. Both of them made it to the New York Times. Most notable 100 books of the year. Then there's Higgs Discovery, and most recently, her work has focused on dark matter. So there is a book called Dark Matter and the Dinosaurs, which proposes a connection between dark matter and the extinction of dinosaurs on Earth 66 million years ago. How's that for a theoretical physicist? So I think this brings us to the topic of today's colloquium, and I'll stop saying things because it'll be more interesting to hear her talk about darkly charged dark matter. So please welcome Professor Randall.
Well, thank you for that radical and crazy introduction. And I really want to thank Stefan for organizing such a wonderful visit. It's been really, or Professor Alexander. It's been really nice to visit here today. So I've enjoyed meeting with a lot of people here, and it's been really wonderful. I'm going to be telling you about some work I've been doing in dark matter and just generally, a little bit more generally about dark matter. I also will have a confession, which is that my other computer died. So the talk that I thought I was going to build on was on the other computer. So, okay. So we have, so I have 2 mics, okay. So we have a combination.
You have another mic? Oh, you have one. Okay. Then didn't forget it, sorry.
Well, I think the other one's for recording. I don't know. Do you hear me? Do you hear me in the back? Okay.
Forget it, yeah, sorry.
Then I guess it's working. Okay. That's good. So anyway, it's, so this is a combination of sort of an old talk and an updated talk, but it might leave out stuff in the middle. So feel free to ask about anything. But in any case, I just want to talk about where we are with dark matter today and how we're thinking about it and ways that it will be interesting to think about it in the future. So I probably don't need to tell you, but I'm going to tell you anyway, that the universe is mostly made up of stuff that isn't ordinary matter. Ordinary matter is only about 5% of the energy density of the universe. And the rest of it is in two other components that we lump together as dark matter and dark energy. So I'm not going to say anything more about dark energy. Dark energy is just energy spread throughout the universe. It's not in structure. It's actually very hard to study because it's smooth. It's been, in principle, it's been the same over time. It's the same everywhere. But dark matter is interesting because it's matter. It clumps into structures. And as I'll try to argue, that means that we possibly can learn a bit more about what it is by doing not just particle-type experiments, but also astronomical measurements, which I'll try to focus on a little bit as this talk goes on. So I think it's fair to say we have an outstanding cosmological model. It works really well. It predicts other things. And this is really, since they gave away my PhD date, I can say that since that time, I mean, cosmology has really been changed in revolutionary ways. It was something of a science before, but now it's really a science in the sense that we really make precision measurements, and we have precision measurements of these quantities. The fact that we can say something like 25% of the energy density in the universe is in the form of dark matter is really quite an accomplishment, that we can really say the precise numbers or fairly precise numbers, and we'll talk about that. But of course, we don't know what a lot of the stuff is. Now, it's funny because I have given a lot of popular talks for non-scientists, and everyone wants to know, are you sure there's dark matter? Are you sure you didn't get the equations wrong? I mean, I personally don't find it that surprising that we don't know what most of the universe is made up of. I mean, we have pretty finite measuring tools at our disposal, including our senses. So the fact that there should be stuff out there that is not stuff that we can necessarily measure should not be that shocking. In fact, the fact that what we do know about is 5% of the energy density of the universe, I find quite amazing. That's quite significant. But the rest of it, we have yet to find out, and we'll talk about how we might. But I just remind you that the way we see things is, until very recently, all through electromagnetic signals. Gravity waves is a new way of seeing stuff. It's going to be a long time before we see dark matter with gravity waves. It's not sensitive enough, but there is some hope there eventually, I think. But right now, I mean, we see things with light, and so if dark matter, by definition, is matter that interacts with gravity like matter, but by definition is not interacting with light like the matter we're familiar with, it's not that surprising we don't see it. So the question is, what is it, and how can we see it, or how can we learn more about what it is? Okay. So how do we see so far? How do we know about it? Well, we don't know about it because of any light emitted or absorbed. We know about it purely through gravitational influences. But I put this list in to remind you that there's many different ways that we measure it. It's not just one measurement, and all of those agree. And so, people that try to argue for alternative forms of gravity, et cetera, they usually can explain one or maybe two of the things on this list, but they rarely can explain them all. And so it really does look a lot like matter. So let me just remind you what these things are. One of the first ways we knew about dark matter was from galactic rotation curves, the fact that things rotate around as if, and that the speed at which they're rotating doesn't change with the distance from the center. But the fact is the mass enclosed seemed to change because the light goes away. So it really looked like there had to be matter there that's keeping those things rotating that is not in the form of matter that we see. And that was the work of Ford and Rubin and many others who really saw that there really seemed to be something that was not being seen. There's similar kinds of measurements that are done in galaxy clusters being gravitationally balanced states of galaxies, where again, velocities are bigger than can be accounted for by the matter that's actually observed. There's something called gravitational lensing, which has to do with the fact that even though dark matter itself doesn't emit light, it can affect the path of other things that do emit light, and in particular, the light will bend around objects, and it will be sensitive It doesn't care about what kind of matter it is. If there's matter, it will bend. So by looking at gravitational lensing, we also learn about the existence of dark matter, and also, to some extent, the distribution of dark matter, because how things lens will depend on where the intervening dark matter is. One of the things that I find very significant is something called the bullet cluster. There's actually a couple of others like it, which is basically, we just said a cluster of galaxies is a gravitationally bound set of galaxies. It looks like the merging of at least two different clusters. And when those things merge, it looks like the dark matter passes through and the gas that's inside gets left behind. You can actually see visually pictures where you can really see the separation of where the ordinary matter is and where the dark matter is. And why I find that's particularly significant is that is basically what you expect if dark matter is in fact matter. You would expect it to sort of just pass through. And it's very hard to come up with a alternative theory to gravity where that happens. I mean, this is just something that would naturally happen because something is made up of matter. There's other ways that we know about dark matter. I mean, the distant supernovae that are always viewed as ways that we study dark energy. Of course, the reason we could study dark energy with them was because we could also study dark matter with them. So it's really a combination of seeing what their the expansion rate would be based on both dark matter and dark energy. A really important thing, and that's actually what leads to these more precise measurements, is cosmic microwave background radiation. Cosmic microwave background radiation is sensitive to dark matter because what it's measuring is when matter decouples. That is to say, when electrons and protons get together into atoms. And as that happens, there's what's called acoustic oscillations. But radiation drives things out and gravity drives things in. But if you have dark matter as opposed to ordinary matter, the radiation doesn't drive it out. So what allowed things to form earlier at different scales was the existence of dark matter. So, and you can actually measure the amount of dark matter versus baryons versus ordinary matter by measuring the height of different acoustic peaks, okay? So, so that was how we get that number that's 25%, although measurements that were done, say, in galaxy clusters actually came very close to that as well. So we really see evidence that there's about 5 times the amount of energy in dark matter as ordinary matter. But a couple of things that I'd like to point out are also just the very existence of galaxies in the lifetime of the universe. I remember when the COBE satellite made its measurement and first discovered density perturbations. But the fact that density perturbations were as small as they are meant that we had to have had some form of dark matter because structure had to start forming sooner in order for things to go what we say is nonlinear by today. In other words, we wouldn't have structures like galaxies and galaxy clusters even in the first place if there hadn't been more matter than is observable in just the visible universe. We need that matter to start structure forming soon enough that it goes nonlinear by now. And another thing is just the existence of galaxies on the scale of the Milky Way. Had it just been ordinary matter, radiation would have washed out structures on this size. So that's an awful lot of evidence, not just of what we see today, but of how things have evolved over time that points to the existence of dark matter. So I would say that is fairly well established. Okay. A lot of evidence, and it's all consistent. And so people who say this, it's all indirect, well, you know, that's how science is done. You know, we see lots of evidence and we put it together and we say what it means. But there still is this important question, which is, what is it? Now, what does it mean to ask what it is? I mean, clearly it's some form of matter, but what do we mean when we ask what is something? Well, in this case, I think I'd say that what we mean is, first of all, is it made up of some sort of elementary particle, like matter that we know about? It's made up of a bunch of different types of particles. If it is a particle, what is the mass of the particle? What are the interactions or charges? Is it interacting under any forces? But also, is it just one type of particle? Like ordinary matter, there's lots of different types of particles. Maybe there's a bunch of different types of particles. What is it? So we only know about the gravitational interactions. So what else could there be? So, okay. So how are we going to find out? Well, we're going to look for some theoretical and experimental clues. I mean, I met with some students earlier. They asked, you know, sort of, how do you decide what you're going to work on? Well, dark matter is a pretty interesting thing to work on. We know it's there. We know there's lots of measurements going on to try to figure out what it is. but how do we put it together? What are the possibilities? And as I'm going to try to explain, one of the reasons it's interesting to work on dark matter and think about what the models are is that it kind of guides how we do our measurements, what we can look for. And it points to measurements that we could do that we wouldn't have done otherwise. So I can't tell you that any of the ideas I'm going to present are right. In fact, most models are wrong. It's just a fact of life. But it does tell you ways that you can actually do measurements in ways that you actually learn a lot more. So let's think about that. So one of the things is that was a repeat. But one of the things I find interesting is that we say look under the lamppost, but in the case of dark matter, it's literally kind of the right thing to do, in the sense that what I argued a moment ago was that it was really dark matter that allowed for the formation of structure. So basically, dark matter collapses, and also ordinary matter comes along with it. So it's not surprising that when you look for where things are light, which is where ordinary matter is, you should also have dark matter nearby. In other words, if stuff that emits light is clumping, there probably is dark matter that sort of started the existence. Doesn't mean it's distributed exactly the same way, as we'll talk about later. The other interactions do change the detailed distribution. But the fact that, roughly speaking, you should find dark matter and ordinary matter in the same places is not a coincidence. It's because that's how structure formed. Okay? Okay, so one of the most popular possibilities, at least for a long time, was something called WIMPs. One of your department members who's not here, so I'm deliberately embarrassing him, is someone who looks for WIMPs. Someone who looks for WIMPs. And I'd say that until very recently, it was essentially the most popular candidate. Probably some people still really like it. WIMP stands for Weakly Interacting Massive Particle. And why do people like it so much? Well, what are WIMPs? WIMPs are basically particles that occur in extensions of the Standard Model. So probably most of you have heard of the Higgs boson. We generally think or thought that there would be a sector associated with the Higgs boson because we don't understand its mass. So there should be a sector associated with the Higgs boson. We would expect to have other particles with about that mass. And it turns out that if there are particles with about that mass, if you work out what's called this thermal abundance, how much you would have left in a thermal universe where it had a cross-section essentially set by that mass, you would find that it's just about the right amount to be dark matter. Whether it's exactly the right amount depends on the details of the model, but it really is in the right ballpark. So that's good in the first place. I mean, that didn't have to be the case. It could have turned out to be very, very different. But it turns out it's about the right amount, which seems sort of promising. But the real reason that people get excited about this is because if it is an extension of the Standard Model, unlike many of the other possibilities for dark matter, it's something that will interact fairly directly with ordinary matter. Because it's an extension of the Standard Model. So it might not have exactly the same charges as ordinary particles, but it certainly should have some couplings that are overlapping and some interaction. And this has given rise to lots of different ways of searching. So it's looking for things that, even though they don't have electromagnetic interactions, say strength with our particles, they still have some interactions with our particles. Okay, so it's stuff that's not a totally different sector. It's part of our sector. So when people say they're looking for dark matter, at least until now, almost always they've been talking about really looking for WIMPs. So when people say they haven't found dark matter, they usually mean they haven't found WIMPs. And in fact, that's the case. People have not found it yet. And that's probably the biggest demerit for it is that we've looked for it and haven't seen it. Doesn't mean that we will never find it. It could be that in the next 10 years we find it. But if we don't find it in the next 10 years, we probably will not find WIMPs. So let me just remind you how we look for it. This is just very rough, but there are basically three methods that people talk about. I'm going to go through this quickly so I can get to some newer stuff. But people talk about direct detection, which are basically big vats of something. It could be a lot of xenon, for example, which is what's done a lot these days, where you look for. And so the idea is that even though there's a very small interaction cross-section, if you have enough of it, you'd still see something. So you can look for small cross-sections by just having a bigger detector volume. And that's what people do. And we're waiting for even more sensitive searches. People also were hoping that it was really associated with something beyond the Standard Model. So there would be evidence at the Large Hadron Collider, which found the Higgs but hasn't found anything yet beyond the Higgs. So the hope was that we'd find something there, but again, that seems to have been squashed. And finally, there's something which is really interesting called indirect searches, which is the idea that dark matter, if it annihilates, that is to say, if a dark matter particle finds another dark matter particle, it can annihilate and turn into ordinary matter if there is some small interaction. And if it does that, then we have a chance of seeing that. Now, of course, there's lots of ordinary matter in the universe, so you want to look for things that are special, like, for example, antiparticles or photons with a distinctive spectrum. Even antiparticles, there's some production in the universe, but the hope is that you can look for enough of it or distinctive properties that you can tell the difference between this stuff and ordinary matter, and thereby find dark matter. And I should say that even though we probably didn't find dark matter, we did find a lot of interesting stuff about antimatter in the universe by doing these kind of measurements. Okay. So as I said, we haven't had any direct detection, indirect detection, and the LHC hasn't seen it. So what do we do? So it's a mystery. Okay, there's no sign of WIMPs, and there actually is only a sparse sign of new weak scale physics. So what I'm going to try to argue is that if it's not WIMPs, and I'm not going to talk about axions, so some people here might be thinking about axions. That's another possibility where it might have some connection to the Standard Model. But if it doesn't really have a connection to the Standard Model of particle physics, what are we going to look for? And what I'm going to try to argue is that looking for structure in the universe is probably one of the best ways to learn something about dark matter. Doesn't mean we'll know in detail what it is, but if we see interesting details of dark matter, of structure that's formed, it could be some indication that dark matter has some interactions that are interesting, that give it some interesting properties. And I'll tell you about those. Okay. So before I do that, I just want to mention one piece of work which I've done with the student Linda Hu, or I should say Linda Hu did most of the work. We pointed out that there's actually, it wasn't our idea to do this, but there actually are some very interesting searches going on for anti-deuterons, okay? So rather than just antiprotons, anti-deuterons. Now you'd say, well, the cross-section to produce anti-deuterons is going to be really small, and indeed it is. But the interesting thing is that the background for anti-deuterons is also really small, okay? So the background is very small, it's particularly at low energy, because you have to produce so many nucleons. So, and in particular, AMS has looked for it, but there's a satellite called GAPS, which is about to launch within probably a year, where they're going to actually do the search for this anti-deuterons. They have this very interesting method of an excited atom that then can decay, leaving an X-ray signal and doing time of flight measurement to look for anti-deuterons specifically. And so, I actually got excited about this maybe, 7 or 8 years ago. Seemed like a really cool thing. But in the 7 or 8 years since then, it turns out people have done really good measurements of direct detection. So much so that it ruled out a lot of the potentially interesting parameter space for anti-deuterons. So, but the fact is that the launch got delayed. So is there a reason to do it? We're wondering, is there anything they can actually find? And the answer is yes. There's actually a really interesting category of models that they are sort of uniquely positioned to look for, which is something called dark photon dark matter. So let me show you some pictures to illustrate what I mean. So basically, as I said, for most types of WIMPs, we have direct interactions between dark matter and ordinary matter. And the thing is, the same interactions that lead to the annihilation cross-section of dark matter into ordinary matter can also lead to direct detection in general. You just turn the diagram around. So then you can actually have direct detection. Now, the interesting thing is this other possibility where dark matter can annihilate into dark photons. So it's annihilating in its own sector. But then those dark photons can potentially mix with ordinary photons. Now, what's interesting about this scenario is that the annihilation happens right away, but the actual decay is suppressed by the mixing, okay? So the direct detection can be much smaller, because you can have that mixing be very, very small and still have decay in the lifetime of the universe, but you don't have direct detection, okay? So it's a very general class of models in which you very readily satisfy the fact that you haven't had direct detection, but you still could hope to have indirect detection. Because again, all we really know in the sort of WIMP scenario is the annihilation cross-section. Everything is based on that. So the fact that it would lead to direct detection was a consequence of how we assumed this happened. But if it happens through the fact that photons and dark photons mix, you have this interesting possibility. And what's interesting is there's this sort of so people have looked for this kind of stuff at very low energies. A lot of the experiments are done at very low energies, looking for very light dark matter or very light dark photons. But in this sort of tens of GeV range, there's really nothing that's looking for those. And so what's interesting is that we can actually have a really nice, so this is for a photon of 30 GeV, dark matter of 50 GeV, and there's a real possibility that gaps could see some of the parameter space, a sizable part of the parameter space. And in particular, for those of you up with sort of the Fermi signal, it's even possible that one of the models associated with that could be tested by doing this kind of measurement. So it turns out that it actually has this really interesting range that it can do, and it's fairly unique in this respect. So it's very interesting. Okay. So I'm just going to briefly mention another possibility, which is similar in spirit. So with WIMPs, we said that the reason we liked it was because we have about the right amount of energy left at the end of the day. But another thing you might have noticed is that the amount of energy in dark matter is kind of around the same as the amount of energy in ordinary matter. Now, some of you might say, well, that's not true. It's a factor of 5. But a factor of 5 is nothing. It could have been like 1 trillion times more or less. Right? There was no reason that they had to be at all the same. So the fact that the amount of dark matter is at all comparable to the amount of ordinary matter is rather striking. So it might also be some indication of some common origin of ordinary matter and dark matter. So one of the and so we believe ordinary matter is associated with an excess of matter over antimatter. We don't just believe it, there's lots of evidence for it, like the fact that we're all sitting here and not exploding. So we know that there's more matter than antimatter. So some people have suggested maybe the same is true for dark matter. And maybe there's more, and maybe dark matter also has an antiparticle that isn't itself. And maybe there's an excess of dark matter over dark antimatter. And I'm just mentioning that as a possibility because I think it's quite striking and intriguing. And then you might find that the number densities are similar. And this is also something many others worked on, but I worked on with Matt Buckley and something we called exogenesis. And the only thing I want to point out was that it was thought that in that case, the dark matter had to be really light, but it turns out it could be in the sort of the tens of GeV range. And so you could still have this work as a reasonable possibility. So I think this is also an intriguing possibility. But now let's just to say, you know, this is nice, these are nice coincidences, but what if dark matter really is dark in the sense that it really isn't connected to the standard model? All of those possibilities, there was some connection to the standard model. What if that's not the case? Is there anything we can hope to see? And so I would say the answer is yes, if there are interactions in the dark sector. And by that, and I'll go over this a few times, I really mean interactions in the dark sector that our matter doesn't experience. So just the same way we have electromagnetic interactions that dark matter doesn't experience, maybe dark matter has its own electromagnetic or whatever interactions that we don't experience. Now, of course, we're never going to see those directly. We're not charged under those things. They're invisible to us. But what it could do is it could lead to interactions in the dark sector itself that change what structure looks like. So by doing detailed measurements of dark matter in the universe, we can perhaps hope to learn something about whether or not these interactions exist and something more about the dark matter. Okay? So this is what we call self-interacting dark matter that interacts with itself, but not with our matter. And so the good thing about this, in a sense, is that we're just looking at, we're really looking for it gravitationally. We're measuring its properties, which could be come from non-gravitational origin, but we're finding dark matter in the one way we know we can, which is through its gravitational effects. Okay? So we worked on something that we called darkly charged dark matter. So for self-interactions, there's a number of possibilities. It could be that the interactions occur through some heavy objects, But we actually this is work with Pratik Agrawal, Francis Saracine, Jacob Schultz. We actually were interested in the question of, could you have dark matter that really does have its own photon, like its own electromagnetic sector? And naively, that seems extremely dangerous, because you have long-range interactions, you have this light photon in the dark sector. It really seems that it's really constrained. So at first, we thought this was sort of, at least naively, I thought this was kind of an absurd possibility at first. But it turns out that it's actually really hard to see this. And it turns out that the constraints that were on this kind of thing were sort of overstated. So let me just give you an idea of what that means. Okay. So, why was it thought that it was unlikely? What were the existing constraints? So the constraints had to do with what the structure looks like. So one thing people looked at was ellipticity in halos. So, we talk about dark matter being in spherical halos, but actually the halos are slightly elliptical. And the idea was that if dark matter interacted with itself, it would just wash out any ellipticity, so that it would just look so spherical, there would be no triaxiality in it, and you wouldn't see it. So if you see any triaxiality, it is constraining the interactions. That was one possibility. Another thing was the bullet cluster type constraints that I told you about earlier, the bullet cluster. And I said the fact that the dark matter went through is evidence that it's not really interacting. So there's going to be some constraint from that kind of thing, but we'll talk about what that might be. And the last one is actually kind of interesting, and I think something really interesting to follow up, which has to do with which is the survival of dwarf galaxies in halos. So you can have dwarf satellite galaxies. So dwarf galaxies are small galaxies. So in a big galaxy like the Milky Way or other big galaxies, there can be dwarf galaxies that orbit around in that big galaxy. Now, if that's the case, the dwarf galaxy itself has its dark matter, but that dark matter can interact with the dark matter that's in the Milky Way halo or whichever other galaxy you're talking about. And the claim was that that would lead to the evaporation of these dwarf galaxies. So this all seemed to significantly impinge on the parameter space. And the fact is that all of these things are really hard to do, because they're all really depending on what you started off with, what distribution you started off with. So, so what I did with these authors that I mentioned earlier is we just went through all these constraints and we tried to figure out what the real constraints are. And it turns out that all of them were overstated because they make assumptions. And as someone who's done particle physics, for a long time, people would sometimes rule out things or say that this is something you would definitely, if you measured this, you would rule it out. And then they would measure something and they wouldn't find it. They say, well, we made this assumption. And so, it's really important when you say what the constraints are, that you really are saying it within the context of what you're assuming. So in other words, like, what if you found it next week? Then you'd be like, well, I was assuming this, so it's not really true. So with the ellipticity of halos, it turns out it was a really interesting story, because the constraint comes primarily from the ellipticity of galaxies. Galaxy clusters had some constraint, but it was much weaker. And it turns out there was only one galaxy where they measured the ellipticity. And as I'll show you, the ellipticity is very strongly, the measurement is very strongly a function of radius. And that matters a lot, because how much interaction you have depends on where you are. If you're inside, towards the center, you're going to have the densest dark matter and you'll have the most interactions. As you go further out, you'll have less interactions. So, and of course, the measurements of ellipticity are going to be better towards the outer regions. But it turns out there were a whole bunch of other issues that came up in terms of how you do it. And in particular, even how do you predict ellipticity? I mean, you could predict it according to the velocities of what's there, but you could also predict it according to the structure. Like if over time, if there's some non-equilibrium process, something absorbs some other galaxy, that can also induce some sort of triaxiality. So it's really hard to do this, and no one has actually done it right. I mean, you could do some simulations, but there's always assumptions built into that. The bullet cluster type constraints, I mean, it's somewhat arbitrary because you don't know what you started with. So you can say a certain amount of stuff can go through, but you don't know how much was there in the first place. And the survival of dwarf galaxies, again, you sort of don't know what the distribution you started with. So in particular, it might be that this actually works in your favor, because maybe it's getting rid of some cuspy regions or something like that. It's heating up the dwarf galaxies, not necessarily making them evaporate. So it's really not clear. This is mostly what I've said, but this is just to give you an idea of, like, this is the ellipticity as a function of radius, where you put in the actual errors. And you see that near the center, there's basically no measurement at all. And in the outer regions, which is where you don't have that much scattering, you finally get some measurement, but it's not that precise. So it turned out if you just did this in detail, you would go from that sort of yellowish curve to the blue curve. But even this we don't trust, because as I said, this blue dotted curve is mostly based on ellipticity of the galaxy, and we actually don't know how to calculate it. So we just calculated it according to their method, but that's just one source, and so it's not at all clear that that survives. And the other measurements just aren't as strong, like the purple one I believe was from dwarf galaxies. So it's just not that constrained. And what I mean by not that constrained is that you can actually have dark matter be roughly the weak scale, like TeV scale, and have interactions of order electromagnetic strength, and it's still allowed. So you really have this large range of possibility for what dark matter can be. It really can have pretty sizable self-interaction. Now, that's not to say that we'll never know about it, and so this is really more a call out to do these predictions better, which is very challenging for all the reasons I've been saying. Okay, but I say that darkly charged dark matter is clearly viable as a possibility. The constraints on the mass are considerably weaker than were stated, and often not reliable. So I think simulations will help. But I think it is a really interesting possibility that dark matter has its own world of interactions. And that could give rise to lots of, and we're not just saying interactions in this case. We're saying interactions with like a massless gauge boson, like something that's a photon-like. I mean, there's lots of possibilities for self-interactions that we knew were possible. But this is saying that even something as radical as having a photon in the dark sector is still, as far as we know, allowed. And so there's really some, which is good because we're doing lots of measurements of structure, so it would be really good to understand these things better to see what the constraints really are. Okay? And one thing that's just really cool, which is just kind of amusing, there's something called Knudsen number, which has to do with the size of the object versus the mean free path. And it turns out there's a sort of duality, which is to say that, as you would think things get more constrained as they interact more and more. But it turns out that once the interaction gets really strong, it just doesn't travel anywhere. It's so strong that it can't transfer energy. So it turns out that something really strongly interacting can be like something that's really weakly interacting. And so again, I think there's some really interesting theoretical follow-up to happen here, because it means that, and in particular, the reason we cared about this was because the regime that we found was allowed was such that inside dwarf galaxies near the center, where things are moving very slowly, you could actually get interactions that are so strong that you actually care about this. So we were thinking at first that we would rule it out because things were so strong, but it turns out that once the interactions get really strong, the constraints again get weaker, which is a really interesting phenomenon. So that's if all of the dark matter is interacting under this force. But actually, the first thing that we worked on, and this was with Gigi Fan, who's here, Andre Katz and Matt Rees, we actually considered the possibility that only a fraction of the dark matter interacts in what we call partially interacting dark matter, and also double disk dark matter for reasons that will become clear. So we said, rather than assume all of the dark matter is interaction, maybe it's just a fraction. After all, if we look at our matter, not all the matter interacts the same way. Why should we assume that dark matter is just one single particle with just one interaction strength? And of course, saying it's a fraction changes all the constraints and of course makes it much weaker. Because if there's only a fraction of the dark matter that has these interactions, things will be very different, okay? So the conventional constraints are even weaker, and those are for obvious reasons. But there are lots of important implications. Now, why is that? You might say, why would we care if it's only a subdominant component? We don't even know what most of the dark matter is. Why should we care if it's only a fraction of the dark matter? So one reason is that it can be the most relevant for signals. So even if it's only a fraction of the matter, it can be the thing that is easiest to detect some interesting property. Now, why do I say that? Well, let's think about ordinary matter. Ordinary matter, namely baryons. It's only a sixth of the matter in the universe. yet it's basically all we detect. Now, why is that? It's because of all the other ways in which it interacts. So even if it's only a fraction of the dark matter, if it has interactions, maybe it will do something interesting that will make it more noticeable. And I will try to explain what that might be. So, and in particular, one of the things I'm going to be interested in is whether you can actually have a dark matter disk, an actual disk of dark matter. So whereas, so remember I said earlier that ordinary matter and dark matter are pretty much in the same place, but that's obviously not exactly true because where we are now, we have a lot more matter than dark matter. In the galaxy, we have a lot more dark matter than ordinary matter, but where we are, we have a lot more matter. And why is that? Well, the reason is because of all the other interactions, which allow ordinary matter to collapse a lot more. So even before things collapsed into stars and into all the structure that we see here, so dark matter more or less is in a spherical halo because it's not interacting, the first approximation. But ordinary matter, we know, can radiate. And in particular, protons are too heavy to radiate significantly, but electrons do radiate significantly. And because which are lighter. So because electrons radiate significantly, in the lifetime of the universe, or the lifetime of the galaxy, they can collapse. And they collapse into the thing that we see as the Milky Way disk. Okay? And we see it as a disk because orbital angular momentum is conserved. Otherwise, we just collapse all to the center. Okay? So the fact that we see the disk, the Milky Way disk, is precisely because of interactions. So we asked the question, could you also have the same thing happen in the dark sector? Could you have some particle that's like an electron that allows it to collapse? So in the first case that I did, where I said everything interacts with this dark photon, there was no light particle. There was only just this heavy particle that I said is maybe 100 GeV, kind of weak scale mass, or bigger or smaller, just not as light as an electron. If there were a particle as light as an electron, it would have been ruled out by cosmological considerations. But because everything is heavy, it decoupled from ordinary radiation early enough that CMB did not constrain it. However, if we had something as light as the electron, then it couldn't be all of the dark matter, because if it were, it would be badly ruled out by the interactions. So it has to be a fraction, okay? So we have this situation where a fraction of it is this type of matter, but because of that, there's a possibility that a fraction collapses. So in this scenario, most of the dark matter does form the ordinary spherical halo that we're familiar with, but maybe a fraction of it will collapse into a dark disk, okay? Do we know that's there? No, but as I'm going to try to argue, by thinking about it, it tells you a different way to go about the measurements you're doing. And it gives you different targets of what to look for. And we learned some pretty interesting things. Okay. So as I'm going to argue, to some extent, the dissipative fraction really makes you rethink a lot of the constraints that we have. And since we really don't know what dark matter is, I think we should really keep an open mind. And especially if there are things that are getting measured anyway, even if we're not asked them to. All these astrophysical measurements are putting constraints on this anyway, so it's really worth thinking about, okay? Okay, so what do we need? Well, we need to have, again, darkly charged dark matter. So we need some form of radiation. So the model is very simple. You could ignore most of these symbols. The model is simply the fact that there is a dark photon, which is what's labeled as U1D. It has its interaction strength, which is labeled by alpha D, which is like our alpha electromagnetic. And there's different particles. There's the heavier dark matter particle, which is called X, which you can think of like a proton. And there's a lighter dark matter particle, which has opposite charge, which is called C, which stands for coolant. It's like an electron, okay? So then basically, you can have both thermal and non-thermal components, and you can end up with both of them. And I'm not going to go through all the details, but basically, you can work out the radiation through Bremsstrahlung radiation. Bremsstrahlung is redundant, and inverse Compton scattering. And you can find out the parameter space that would actually lead to a dark matter disk. And you find, not too surprisingly, that the parameter space isn't that different from what we have in the standard model. It's basically, you find that alpha is, roughly speaking, alpha electromagnetic, and the mass is, to within a factor of, say, 10 or 100, is about an electron mass. You need something light, and you need something that interacts electromagnetically. But if you have that, then you could also form a dark matter disk. So does that exist? Is it there? So when we first wrote this, it was really frustrating. It was basically, astronomers said, well, there's a paper that says ruled out. Now, first of all, anyone who does measurements knows that you can't rule it out. All you could do is put a constraint, right? You're always going to have room for some other lower surface density. But in addition to that, what they meant by ruled out was really, we don't need this. We can fit the data without assuming there's a dark matter disk, which is fine. But imagine if we did particle physics like that. We would never find anything new because basically the way we find new things is we say what distinguishes them, what are the little effects that we can see. So usually we're just putting constraints on what's new, and that's how we learn new things. But sometimes we find them. So in this case, it turns out, again, unless you really target and look for this dark matter disk, you probably would miss it. And I'll try to explain why you really need to do that in some of the work that we did, and actually Gigi Fan's group has done as well, to look for this kind of dark matter disk. So, but one thing I want to mention, which was kind of cool, which I hadn't anticipated, was we knew that, you can ignore most of this, I'll just tell you the punchline, which is that the thickness of the disk in this very simple approximation where we just have radiation and we allow it to cool, and we say that the parameters are similar to the parameters of the standard model, that is to say, similar to the electron mass, similar to alpha electromagnetic. If you assume that, then the temperature that you get to will be about the same. But if your dark matter particle is heavier than the proton, that means that mv squared, the velocity, will be lower. Okay, so you have some non-relativistic particle with some fixed temperature. It's going to be lower velocity. And also, if it has a bigger mass, it will have lower density. So the combination of these two effects turns out to mean that, at least at this simple approximation, the thickness of the disk scales inversely to the mass of the particle. Okay? So if you have something heavier than the proton, you would expect not just to find a disk, but you'd expect to find a disk that is more narrow than the ordinary disk from baryons. So there'd be this. So even though you have this small fraction of dark matter particles, it can actually form a denser disk because it's narrow if it's heavier. So again, the summary of the model is just there's a heavy component, and then there's a light component that radiates. There's a U1, and then we expect a dark disk for some region of parameter space. Okay. And again, it could be much denser and probably tilted with respect to errors, but probably it's going to align. You can show that it's going to align. And the signals can be rich. So how do you find it? Well, what do? Well, it turns out that if you actually knew, just using, you can just figure out what the gravitational potential is. If you have this dark disk of dark matter, you can just work out the gravitational potential. So if you measure the velocities and the density distribution of all the nearby stars, then you could figure out, is there this disk, by doing this as a function of height above and below the galactic plane. And by the way, that's the kind of measurement that they did, and they found no evidence for the dark disk. But we thought, let's look again and see what we really learned. So one thing you had learned by having a model is that actually the way these constraints were put in wasn't quite right, for a couple of reasons. One is that what we just saw is that there's kind of a couple of parameters. There's sort of how much dark matter there is, but also what is the thickness of the disk, okay? So before, it was always assumed that it was just some sort of extra component of an existing component. So I should just clarify that when we talk about the Milky Way disk, it's really composed of several different components. There's sort of stars, but there's gas, and there's cold gas, and there's hot gas. There's different components, each of which can be treated separately. So when we do these kinematical measurements that I just mentioned, where you measure densities and velocities, you're just putting a constraint on sort of the overall density, but then you have to figure out how much there is in ordinary components to figure out how much is left that could be in the dark matter component, okay? But the component of the dark matter disk can have a different thickness than the component of any of these other components of the Milky Way disk. And before, it was just assumed that it was sort of an add-on to one of the existing kind of gaseous components. But another thing that was really interesting, and I should say that I did this work with Eric Kramer, who was a student at the time, is that you have to do it self-consistently because each of the components, it's gravity. So if you have an extra component of a dark matter disk, it's actually going to change the distribution of the ordinary components in a way that isn't taken into account if you just say at the end, how much error do I have? So it turns out that it's actually a very interesting and subtle measurement to do and or also prediction to do. And it's not that easy. So this is what I've been talking about, to how you get the bound from structure by measuring the gravitational potential. So I just mentioned that before our work, Flynn and Holberg used Hipparcos data, and we did that too, but the follow-up work by Gigi Fan and her collaborators and also another group had to do with Gaia data, which I'll come back to in a minute. But the general lesson from what I just said is that there really is a role for particle physics kind of ways of thinking in astronomy. Because what do particle physicists do? By having a model, you target what you're looking for. And that's the way we found things. That's how come we found the Higgs boson. If we didn't know what we were looking for, it would just have been lost in the background. But the fact is that we knew what we were looking for, which allowed us to do a much more detailed measurement. And that's, I'd say the same is true in many cases in astronomy. So by having models, even if you think they're stupid models and they're going to get ruled out anyway, you learn a lot more by studying them. And maybe one day we'll even find something. Okay. And just to give you some idea, these are some tracer populations. And one of the is with a disk and one is without a disk. And you just look, you can see it's pretty hard to put this constraint on it. And one of the interesting things, Donna, talking to Gigi Fan earlier, is that even using Gaia data. So why is this exciting? Well, so Gaia is measuring 1 billion stars in the Milky Way. It seemed like the perfect measurement. We were so excited when we first wrote our paper because we had never heard of Gaia when we were writing our paper. But then Gaia was actually about to launch that very fall. And usually with particle physics, you have some great idea, but then it's like 20 years down the road when they might test it. We're like, wow, they're going to test this right away within the next 5 years. So, and because they were going to do exactly this measurement, measuring 1 billion stars, measuring their position and velocities. So these guys followed up and said, look, Gaia is measuring it. What are we learning? And so naively, it actually looks like there were stronger constraints. It looks like there were pretty strong constraints. But one of the things that Eric and I learned when we did our analysis was the assumption that you're in equilibrium turns out to be really important. Because what you do is you say you're in equilibrium. So if I know the distribution of dark matter disk, I know all the other components to some extent, then I can figure out what I expect. But if it turns out that your tracer components are moving, then first of all, it just changes your data set because you have to make sure that you have something in the fiducial volume. But it also just changes how you would put the constraint. So if things are not in equilibrium, or if you don't know where they're located with respect to the equilibrium position, it changes things quite a bit. So let me just show you some results that is from the Fan group. And you see that there are constraints on the dark matter surface density versus the disk height, which are quite interesting. But you also see something really interesting in this table. So if you look at the last column of that table, it is the position of the height of the sun. Okay? So Gaia is measuring stars in the vicinity of the sun, in the vicinity of the solar system. And you see that you find very different values depending on which population of stars you look at, which is either an indication of something's really in non-equilibrium, or it's just saying that we don't know where this disk is that we're putting a constraint on. So even if we're putting a constraint, it's not clear how to interpret that measurement. And it's very likely that things aren't in equilibrium, which would explain why we're seeing such different values. But another thing is that just the actual values themselves change from DR1 to DR2 with very small changes in the velocities. So there's clearly something weird going on when we're trying to put this constraint. So it might be telling us that this method, although it seems so beautiful, doesn't work for these populations of stars. And it would be really interesting to follow up and understand why. And just as a curiosity, the Schultz group, which actually really claims they have a constraint, they get an even different value for the position of the sun. So it's just clear that something is not reliable here. So if you were to say that you're ruling something out based on this measurement, you'd be hard-pressed to explain it because you'd have to explain also this discrepancy of solar heights. So I'd say that it's a really interesting situation, a very frustrating situation, where we don't know how to go beyond this right now, like in terms of just this particular measurement. So in light of that, I'm just going to mention a couple of other ways that we might hope to constrain or learn about a dark disk that I've been thinking about. And there's probably lots more, and I encourage you to think about them. So one of the things I did with student Linda Hu, who I mentioned earlier, is ask the question of, for dwarf galaxies, so dwarf galaxies have been measured to be elliptical, but are they oblate or prolate? And the reason that's interesting is that simulations seem to indicate they're prolate, so cigar-shaped versus oblate, which is like, dish-shaped, okay? But of course, if they're oblate, that could be some indication of some sort of disc-like structure. So it's really interesting to ask that question. Now, of course, we only get two-dimensional projections, so how do you actually figure out what the three-dimensional is? So you could look for correlations with surface brightness and velocities. And if you do that, you find when you look at the heavier ones, that is to say the ones for which really what I mean is large mass to light ratio, you find that they are in some statistically significant disagreement in terms of whether you're predicting oblate or prolate. And so it turns out that for these ones that have mass to light ratio greater than 100, there is some indication of deviation from the standard dark matter model. Will this hold up? This is a test of time? I don't know, but people working at dwarf galaxies, I think it's a super interesting thing to look at that people have not looked at yet. Again, I didn't mention this in the beginning, but of course, right now, people are looking for all sorts of ways to see deviations of cold dark matter models from predictions. Are things cuspy versus chord? What is the number of satellites? And all of these things, there's confusion from baryonic feedback, et cetera. So it's really interesting to have different methods for trying to test the standard dark matter scenario. And so this might well be another one. And as I'm showing you, at least preliminary, it looks like, at least for large mass to light ratios, it's not agreeing with what's predicted from the simulations. Of course, it's from limited simulations, limited measurements, and both of these can be done better. But it certainly looks like a very intriguing measurement. Okay. Another thing that I did with Jacob Schultz is thinking about satellites of the Andromeda galaxy. This seems to be this very large plane of satellites in the Andromeda galaxy, which is really hard to explain if those satellites, which is to say those objects, have a lot of dark matter in them. Because the standard explanation is that there are tidal forces, there's a merging of galaxies. Tidal forces pull stuff out of the disk, and then those can form satellite galaxies. But if there's no dark matter in them, clearly what you form won't have dark matter. And furthermore, it won't be heavily dark matter dominated. Now the interesting thing is if there is this dark matter disk, even if it's only a fraction of the dark matter, it could still dominate in the satellites because the velocities are smaller. Remember, that was the temperature being the same, velocities being smaller, which means it's more likely to get bound up. So even though there's less of it, in the end of the day, it could conceivably explain these satellite galaxies, and that's what this shows, just the fraction that gets bound up in the dark matter. And since it was mentioned in my book, Dark Matter and the Dinosaurs, because I figured someone would mention it, I will mention what that is based on. So this is obviously, this really is one of the kookier ideas, but it was really fun to learn about it. And it's also, it does give a target and it gives something interesting to look for. So the idea is that, here's the thought, okay? So it's actually, there's really, really strong evidence, and actually it was really interesting to learn about this, that the last extinction, the last major mass extinction, 66 million years ago, was caused by a giant object hitting the Earth. And, 20 kilometers in circumference, okay? Actually, 20 kilometers big, I think. So it gave rise to some, like, enormous crater. Actually, I think it was about 15 kilometers big. And it gave rise to an enormous crater in the Yucatan. And it's actually really interesting because it turns out that over the course of time, like lots of stuff has hit the Earth. You look at the moon, you see it's all cratered, but most of that was from the early time, the late heavy bombardment. But there's also stuff that's hit the Earth over time. And most of the stuff that hits isn't that big. But if you actually go to there's actually a database on the web where you can see what all the craters are that are on the surface of the Earth. And this is something I did with Matt Reese. And we looked and we saw that there were roughly 20 or 25 craters, I forgot the exact number, that are big, that hit within the last 250 million years. And there was this big debate in the literature of whether those things elicited or exhibited any periodicity. Did these happen on a regular basis? And there are lots of papers that said yes, and lots of papers that said no. But it turned out that a lot of the reason they disagreed was because what particle physicists call the look elsewhere effect. You know, if you look hard enough, if you allow any periodicity, you know, you could end up with something that looks better. But we had a model, right? We have this model of the dark disk. So we can ask, given a model of the dark disk, do things do better in terms of matching the data? So just to give you some idea, I should say, why should we expect to see anything periodic in terms of cratering? So the idea is that as the solar system goes around the galaxy, it goes up and down through the galactic plane. And if there's this dense disk in the middle, when it goes through this dense disk, it could trigger objects being ejected from what's called the Oort cloud. So in our galaxy, we know about planets, we know about asteroids, we know about comets, but it turns out that tens of thousands of times farther away, there are objects called Oort cloud objects, which are what turn into long period comets. Okay? And those are obviously much more weakly bound stuff that's out there. And people had actually thought about this already as a source of these craters or whatever, or things hitting. But the problem is if you just use the ordinary Milky Way disk, first of all, it wasn't dense enough. And second of all, it just didn't have enough stuff in it. So it was too thick, and it didn't have enough stuff. But if you think about it, the dark disk can solve both those problems, because there's both more surface density and also a more emphatic kick that you get because it's narrower. So we put this in, and we found that, indeed, it did match the data better. And if you do it, you actually get, and this is where sort of one of the targets for what to look for the dark disk comes from. I mean, this is just one target. It's interesting no matter what it is. But you see that somewhere between 10 solar masses per parsec squared, you would agree better with the data once you put in. So if you leave out this periodicity, you'd probably favor no dark disk. But with this periodicity, you actually favor a dark disk, which is kind of intriguing. Does that mean it's right? No. But it gave us a target of what to look for in the Gaia data, which, as I said, has been frustrating because we don't know if we can trust what's been done. I mean, naively, it looks like it would rule it out, but we don't trust it because we don't know. Because this question of the solar heights and the fact that it varies so much really does give reason to question the data. But the reason we did it, even though it sounds so crazy, is because it really is real science. You can actually match the data. You can predict what you should see. You should predict what the consequences should be if this is right. So we don't yet know if it's right. But you know, even the story of just how it was figured out, I mean, this is something I actually talk about in the book, which I hadn't known. But even the story of how we found out that it actually was an object hitting the Earth. I mean, at the time, you know, a physicist suggested it. And well, a physicist and a geologist suggested it. But people thought it was kind of a crazy idea. I mean, you know, and if you think about it, it really does sound like, I mean, if you give public lectures, you know, the kind of thing an 8-year-old will come up. Like, you know, what if a big object hit the Earth and caused the extinction? It sounds nuts. But then it turns out that over the course of time, people really were able to look and find, first of all, the crater hadn't been seen. They found the crater. It was the right size. The story of how they found it was amazing. All the evidence that it really was something hitting the Earth. And it was actually a really interesting story, too, because it was around the time people were worried a lot about nuclear weapons, which we should always be, but we were worried about it then. So people were studying it. So they actually knew what the effects would be because they had been studying the effects of nuclear bombs, and a lot of the effects are really similar. So the whole story of how they found that out was pretty interesting, and that seemed like a crazy idea. So this is not to say you should work on all crazy ideas, but you should work on crazy ideas that can be tested scientifically, which I'd like to think this is one. So for the future, clearly this is a new arena. I mean, we don't know what dark matter is, but we're doing lots of measurements. And there's just lots of there's room for simulations, there's room for thinking about things in different ways. With Gaia, we have much better kinematics. It's a big program. Dark matter being charged is clearly a possibility, but it's hard. And so I think all the measurements I talked about in the beginning, we can do them. I mean, there's a reason people thought there are constraints, but we want to find out what the constraints really are, and maybe even make a discovery. And I think the convergence of large data sets, numerical methods, is really interesting in terms of looking for things, but I would also argue that it's important to have targets. So that's one of the reasons we like to do this kind of model building. So there's lots of new data, lots of new analyses, and lots to think about. So who knows, maybe it'll be the dawn of a new era in dark matter. So thank you.
All right, I'm sure there are lots of questions.
Whenever anyone says that, there's never any questions. I'm sure there are no questions. Okay, go ahead.
Thank you, Lisa. Great talk. This
Thanks.
idea about the dark matter disk being not aligned with our matter, one would suggest that maybe something like a recession process might go on with the axis of the rotation of our galaxy. And what does that actually do in this situation? Or has anyone thought about it?
Yeah, so this is actually something we were talking about earlier, not quite this, but, so you could say, why should they be even aligned in the first place? And the reason we thought they should be aligned is because there should be some gravitational interaction between them. But no one has ever worked, including us, worked out like how it dissipates so that they actually end up aligned at the end of the day. And on top of that, there are different things that can kick things. So that's really, really an interesting question. It's really worth looking at that. And this isn't even just saying they're not aligned, it's saying that they're at different heights. So it could be one population is, just oscillating with respect to another. And, I think that's one of the things that we keep finding when we look at the data from Gaia and elsewhere, is that many more, and including our solar system, that was one of the interesting things we found. There's just much more stuff in motion than we want to think is true. So stuff just isn't in equilibrium. And so working out the consequences of that is challenging, but really important. Absolutely. Yeah.
So I wanted to ask about gravitational effects on the dark disk from stuff in the bright disk. So, old stars have a larger quasar maturity because
Right.
of gravitational attraction. Wouldn't that affect?
So this is a really important question of, and this is one of the biggest loopholes in the analysis, to be quite honest, is, does the stuff stay as gas, or does it collapse into objects? Does it fragment? And so one might think that the instabilities would cause things to fragment, in which case it would do what you're saying. Or if it stays as gas, like as we know, the gaseous stuff doesn't spread out. So it's really a question of whether. And so we decided it's a hard problem, so we'll leave it for measurements and see whether we find it. But it's still interesting to think about it.
In the next couple of years, there'll be experiments in neutrino physics on neutrinoless double beta decay and long baseline neutrino experiments. So we'll find out perhaps whether there's CP conservation or not in the neutrino sector. And I wonder in these light particle models, if that turns out to be the case, there is CP violation, and it changes the picture of what antiprotons and protons in the cosmic background is. Does that affect any of this?
So first of all, as you know, most CP violation has been pretty small. The CP violation, it's big perhaps in some heavy sector or something like that. I'm less optimistic about what we're going to learn by measuring CP violation, because to first approximation, I'm just going to take it for granted that there is CP violation anywhere there can be CP violation. There's no reason for there not to be. There is a strong CP problem. We don't know why it isn't there. But you can just, it's not something that we've never thought about. Like we can think that what happens if there's CP violation, what happens if there isn't. And on the whole, it's not going to change things too much. Because most of these things have so many parameters in them already that, and also if it's a simple model, a lot of the time you can rotate away the CP violation. So it depends on how complex your sector is, whether it's a phase that you can get rid of or not. So it's interesting to think about, but I don't know that there's that much we're going to learn about that, unfortunately. Yeah.
So to this dinosaur thing, like a lot.
Oh yeah, I forgot to mention that. Of course, the dinosaurs and a lot of other stuff got killed.
It's like,
Yeah.
so how would you distinguish between an interaction of the sun with the disk giving rise to this excess ray? So distinguish between the disk and an interaction with halos in the limit of a highly granular halo. And I'm talking about the limit where structure can form at a very, very small scale.
So I'm not sure where your picture is. So what do you, give me a
The
more
halo is
complete.
composed of very, very many small halos,
Okay.
highly granular.
Yeah.
High granularity, right? So, and you get that in cases where you have some very, very small mean-free path.
Okay.
Right? So, if you have interactions between the sun and these other highly dense regions, you could lead to the same effect.
Well, why would it be periodic? I mean, in that case, you.
Well, it will be, we can only have 20
Oh, you can say it's not periodic. I mean, so I should say the likelihood.
Sample the distribution.
It's possible, but then you'd have to make sure that you're, I mean, it's a detailed question of whether the separation is right, whether you get, the other thing is like it would have to happen very suddenly, which might well happen. But you would need a particular separation of those objects, so I just don't know if it would work for the right parameter range. It's a detailed question. Because you need to make sure that,
Separation based on the fractional.
right, you'd have to have the right average separation, you'd have to have the right interaction cross-section, and that's not clear that you have a big interaction cross-section. It's just, you just have to work it out. I mean, it's just not obvious. So I should say that it's not as simple, let me just say one more thing, sorry. It's not as simple as something, I didn't go through the details, but it's not as simple as just an interaction that kicks. What happens is you basically get tidal forces. So as it's going through, it's sort of just pulled out of its orbit. So that kind of thing might happen here too. So
the only thing that, the current thing is the gravitational potential gradient.
yeah.
If that's what keeps running.
Yeah, so then I guess you're saying I guess I don't see why, even if it was granular, it would be regular. So then, again, you can just say, well, statistically, maybe it looks like that, and that's possible. But there certainly is no reason for it to be evenly spaced, although it's probably the simplest model to work out. So then it's not clear that it would be periodic. And I should say, Eric and another student worked out in even more detail afterwards, and it does seem to really agree with the last thing hitting. And also, you'd want a model where you can predict that this one actually was one of the ones where it hit. I guess what I would just say is that you might be able to make that work. It would be interesting to see, but it's not clear how predictive it is because you're going to just adjust your distribution so that it fits. And so the question is, how constrained is it? But it's also interesting. It would be cool if it worked, though. I don't know the answer to that. Yeah.
So you spent a lot of your career, not a lot, but a good part of it, working on the hierarchy problem, meaning the difference between the strength of the gravitation and the weak interaction. Are you, given the new ways of thinking, you're thinking about dark matter, is it still out of the realm to think that working in this type of charged dark sector that there might still be, because it's about gravity and weak interaction in a different way, non-waves, that you might be able to, there might be some connection between that now dark sector
Yeah.
and hierarchy? I'm just even thought deeply about both.
I mean, the only thing I can say is people have just begun to think about sort of, could there be dynamical explanations of the hierarchy problem? I mean, I certainly haven't done that, but I think it's an interesting question. Is there a reason that, we just end up in a vacuum that where the Higgs boson is stabilized, even though if you just wrote down the static thing, you might not have expected that. But beyond that, I don't have that much to say. But it certainly would be great, but it's just, so far, it's just nothing seems to really point to that direction.